So chapter 8, what I want to finish off with is talking about the bonds themselves. And so this is kind of giving you some background as to this understanding of resonance structures and other things that we can now measure and discuss. So when we're looking at bonds, we could talk about what we call bond length versus bond strength. And again, strength, what we're talking about is the potential energy stored in that bond. So bond length, again, is the distance between the nuclei and the bond. Bond energy is the change in enthalpy. Again, this is H, needed to break the bond in 1 mole of a gas. So again, when we talk about stored energy, that's our bond energy that we're talking about. So if we look at single bond, so carbon is going to be the easiest example for this discussion. Single bonds are going to have the least amount of stored energy, and again, you're talking about a bond, again, is the attractive force between those electrons that keep them in there. Double bond and then the triple bond increases in strength or more and more energy. And we saw that when we did some calculations before having to do with bond energy. So if we have that table, you will see that when you have multiple bonds, you have more and more energy stored in there. Then when we talk about length, it then goes the opposite way, meaning a triple bond, because there's such a strong force, those nuclei are much closer together. So if I look at the carbon-to-carbon bond in a triple bond, a double, or a single bond, I see that the length increases as I have less and less of those bonds. So when I talk about some of these bonds, I also like to bring out this table. And the reason I like this table is it kind of gives you numbers or things to look at to kind of say, okay, what are we talking about in terms of bond length versus bond strength, and really get into a better understanding of what we're looking at here. So when I look at this table here, I have HF compared to, let's say, HI, okay? So if I look at the bond length, and this is in angstroms, and again, it's just a unit that we sometimes use for bond length. I have a bond length of about 0.92 versus 1.61. And that is because, again, iodine is bigger, it has more energy levels, so therefore it is a bigger bond because the hydrogen cannot get that close to the iodine nuclei. If you look at the electronegativity difference, that's also an interesting discussion because, again, fluorine is the most electronegative, so that difference is going to be higher in that bond than it is here. So therefore, there's a stronger force that we're talking about. Now, one thing that we don't really calculate, but it is something you can do, and the book does go over, is something called a dipole moment. So what it has to do with is, again, if you were to draw the dipole arrow, if you were to draw it quantitatively, kind of like vectors, you would see that the HF, that would be a longer arrow, and this would be a shorter arrow, okay? Just because of the strength of what's in that bond. Again, we're not gonna worry about calculating this or anything, but it is in your book to talk about it. So I thought this wasn't a bad table to talk about, again, some electronegativity, and we're gonna talk a little bit more about that in terms of polarity, but then the bond length themselves. All right, so the last thing I'm going to finish up in chapter 8, and then we'll go on to chapter 9, is something called formal charge. With formal charge, what I want to mention is this is a way that we can organize the atoms in a molecule. So who is the central atom, where should it go, and those kinds of things. So if we are doing it according to formal charge, there is a formula that you use. And I'm going to have an additional presentation. A former student of mine really liked formal charge, and so he did a whole presentation on formal charge. So a formal charge is always going to be all of the valence electrons minus what we call the bonding, minus 1/2 the bonding electrons minus the non-bonding electrons. So if I have HCNO, How does it really organize itself? I could put multiple bonds in multiple different places. So how does it actually work? So because I typed this up, please include the lone pairs on oxygen here on the one on the left. And then here, put a lone pair on carbon, and then put 2 lone pairs on the oxygen. All right, so I am going to determine which structure is correct, being the fact that I can put a triple bond or I could have 2 double bonds. What is the correct way to do it? So what you do is you essentially go through each atom and count up their valence electrons and go through this formula. So carbon has 4 valence electrons. It has, in this structure, a total of 8 bonds, 8 electrons around it. I have 0 lone pairs on the carbon in this molecule. So I have a, if I add this up, subtract it, I get a 0 for that. Nitrogen has 5 valence electrons minus 1/2. It has 4 lines around it, so that's 8 valence electrons. It has no lone pairs, so it's going to have an overall formal charge of 1. Then if I look at oxygen, oxygen has 6 valence electrons minus. It only has 1 bond, so it's only going to be 2 there. And then I have a total of 6 lone pairs on the oxygen. So that's going to give me a -1. And then finally, hydrogen, I'm going to have only 1. I have 1 bond and no lone pair, so that's going to end up as 0. Okay, so this is the formal charge formula that we can do for each one of those. I'm going to do the exact same thing for this structure over here. So I have 4 minus. Now carbon in this one only has 3 bonds around it, so it's going to be minus 1/2 6. 1/2 times 6 minus 2 because I have a lone pair on it, so I get a -1 for carbons for that one. So this one is 5 minus 1/2 8 minus 0. Nitrogen doesn't really change. It does have 2 double bonds, but it doesn't change in terms of this formula. Oxygen is 6 minus 1/2, but oxygen has a double bond now, and it has 2 sets of lone pairs. So this is going to become a formal charge of 0. And finally, hydrogen doesn't really change, and usually hydrogen, because it only makes 1 bond, can really only be a formal charge of 0 anyway, so it's really no difference there. So when I look at this, okay, there is a series of rules that you want to look at, and the first rule is that they all add up. If there is a difference in how they add up, you take the one that adds up to a lower number. The other thing you want to look at is what we call the most electronegative element that we have. So if we look at where oxygen is on the periodic table, it is more electronegative than nitrogen or carbon. So we want the negative charge, if we are to have one, on the more electronegative element. So that is why this is the structure that you are going to say is the most stable structure for this particular combination. So there's a whole other presentation, so take some time to look through that. This was just a quick example, I thought, but it's usually going to be the electronegative element is going to want the most negative charge.